Hello everyone, I welcome you all for today's session. Right, in today's session, we'll be dealing with the remaining formulas which we are going to use in analytical method in order to find the stress and strains. Right. So in the last class, we are done with two formulas which are normal stress on oblique plane, shear stress on oblique plane, and also what are the sign conventions. In today's class, let us check how to identify the location of principal plane. Right? So let us start with the today's lecture. So I am interested in how to locate principal plane. How to locate principal plane. Right? Now for this, I will make use of the definition of principal plane. Definition of principal plane. Right, so what is the definition of principal plane? Any oblique plane on which shear stress is 0. Any oblique plane on which shear stress is 0, we call it as principal plane. Right, so that we have already studied. Now, in order to get the location of principal plane, what I do in the above equation, that is in this shear stress equation, I will put the value of shear stress as 0. Why? Because principal plane is an oblique plane on which shear stress value will be 0. Right? For that reason, I will put the value of shear stress as 0 in this equation. Right? And let me find out what are the consequences. So 0 is equal to minus sigma x minus sigma y divided by 2 sine 2 theta plus tau xy cos 2 theta. Right? Now this minus term I will take it on to the other side. So it will be sigma x minus sigma y divided by 2 into cos 2 theta is equal to tau xy into, this is sine 2 theta. This is sine 2 theta is equal to tau xy cos 2 theta. Right? Now, therefore, sine theta, this value divided by cos 2 theta is equal to, you multiply this onto that side, 2 tau xy divided by sigma x minus sigma y. So sine divided by cos is tan. Right? So it is tan 2 theta is equal to 2 tau xy divided by sigma x minus sigma y. So therefore 2 theta is equal to tan inverse. 2 theta is equal to tan inverse of 2 tau xy divided by sigma x minus sigma y. Right? So therefore theta is equal to 1 by 2. Theta is equal to 1 by 2 tan inverse 2 tau xy divided by sigma x minus sigma y. Right, so this is the value of theta which gives me the location of principal plane. I repeat, this is the value of theta which gives me the location of principal plane, and that is the reason I call this value as theta P1. Theta P1. P stands for principal plane. So this is giving the location of principal plane. I am writing 1. Reason for writing 1 is, I have already told you there are two mutually perpendicular principal planes. Right? So I have already told you there are two mutually perpendicular principal planes. Right? So this is the angle of or location of first principal plane. The location of second principal plane, which is theta P2, is given by theta P1 plus 90 degrees. This is also important, right? So later we are going to prove this. It is asked many times in the examination that the two principal planes are orthogonal. You need to prove that, right? Or you need to show that the angle between two principal planes is 90 degrees, right? So this will be proving it later. For time being, we need to remember that once if I get theta P1, I can easily get theta P2 by adding 90 degree to that value, right? So this is locating principal plane. Next, last analytical thing which is required is how to locate a plane of maximum shear stress, right? How to locate a plane of maximum shear stress. I am telling you all these things because these are the part of the numericals. Once if you take up a numerical, you will get to know why I told you all these things, and all these things come under the category of analytical approach or analytical method because we are making use of formulas, right? So how to locate a plane of maximum shear stress. Now keep in mind, I am just locating a plane of maximum shear stress, right? I am just locating a plane of maximum shear stress. This plane is not a principal plane. This plane is not a principal plane, right? So to locate this plane, to locate this oblique plane where shear stress is maximum, I use the concept of maxima and minima. I use the concept of maxima and minima. That is, in the shear stress equation which I considered at the starting of the class, I will put d tau divided by d theta is equal to 0. I will differentiate that equation with respect to theta and I will equate it to 0. Right? Which is that equation? The equation is, I'll just write the equation here. Tau is equal to minus sigma x minus sigma y divided by 2 sine 2 theta plus tau xy cos 2 theta. Right? So this is the expression for tau. I need to differentiate this with respect to theta and equate it to 0. Okay, so let us differentiate this. If I go ahead with the differentiation part, minus sign I'll keep it as it is. I'll keep the minus sign as it is. Sigma x minus sigma y divided by 2 sine 2 theta. Derivative is cos 2 theta into coefficient of theta which is 2. Right? Plus sign as it is. Tau xy as it is. Derivative of cos 2 theta is sine 2 theta into 2 with a negative sign. Right? Cos theta derivative is minus sine theta. So minus sine theta and coefficient of theta is 2. I have written it as it is. So this should be equated to 0. So if I proceed further, what I'll be getting here is, I'll take this term towards the right side. So here you are having minus. So minus 2 tau xy into sine 2 theta is equal to sigma x minus sigma y divided by 2 into 2 cos 2 theta. This is what I am getting. Right? So thereafter, this 2 and this 2 you can cancel it. Right? So I am interested in theta. So what I'll do, sine 2 theta divided by cos 2 theta. I have taken this cos towards this side. Now it becomes sigma x minus sigma y divided by this value, sigma x minus sigma y divided by minus 2 tau xy, right? So this is sine divided by cos. It gives me tan 2 theta is equal to sigma x minus sigma y divided by minus 2 tau xy, right? So in order to find out theta, so therefore theta is equal to, theta is given by 1 by 2 tan inverse of 1 by 2 tan inverse of sigma x minus sigma y divided by minus 2 tau xy, right? Minus 2 tau xy. Right? So this is the location of a plane where shear stress is maximum. Location of a plane where shear stress is maximum. Okay, so once if you are done with this, the last part in the analytical approach is principal stresses. Right, to know the formula for principal stresses. The formulas which we are using for principal stresses are written as sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus or minus square root of sigma x minus sigma y divided by 2 the whole square plus tau xy the whole square. Right, so this formula gives me the value of principal stresses. I am writing it as sigma 1 comma 2. Why? I know there are two principal planes. It means there are two principal stresses. So sigma 1 indicates one principal stress. Sigma 2 indicates another principal stress. Right? So where sigma 1 is major principal stress and sigma 2 is minor principal stress. Right, major principal stress and minor principal stress. So this, how you decide that sigma 1 is major principal, sigma 2 is minor principal? Is it always remaining fixed? Okay, it is to be decided on magnitude only. Do not consider the sign associated. Right? Do not consider the sign associated. Why? Because sigma 1 and sigma 2, if they are coming with the sign, it simply means that it is either tensile or it is compressive. Right? So the signs indicate the nature, whether it is tensile or it is compressive. But in order to decide major is nothing but which is having more weightage, which is dominant, and minor is one which is having less weightage. So that is the reason, in order to decide that, I just make use of magnitude and I am not going to consider the associated signs. For example, if I take up an example where in this formula, if I get sigma 1 comma 2 is equal to 44 plus or minus 4, right? 44 is the value of this term, plus or minus as it is, and the value of the under root term is 4. Now in this case, sigma 1 is 44 plus 4, which is 48 Newton per meter square, and sigma 2 is 44 minus 4, which is 40 Newton per meter square. Right? So in this case, what I can say here is, considering the magnitudes, So this is major principal stress and this is minor principal stress, right? Now the same example, let me alter it. What if I am getting something of this sort? Sigma 1 comma 2, this is example number 1. Example number 2, for the same equation, if I am getting it as minus 42 plus or minus 4, right? In that case, sigma 1 will be minus 42 plus 4, which is minus 38 Newton per meter square, and sigma 2 will be minus 42 minus 4, minus 46 Newton per meter square. Now, when you are having some values of such type, be careful. I told you, if you go mathematically, please pay attention, if you go mathematically, you feel that because you are having negative signs, 38 is greater than 46. Okay, so don't apply that logic here. Here, signs are just telling that sigma 1 and sigma 2 are compressive in nature. So, remember this, I am just going to use the magnitude. I am going to decide on the magnitude. So, here also, this is my major, right? Here also, this becomes my major principal stress and this becomes my minor principal stress, right? So this is what you need to keep in mind when you get the values, right? Because it is important, you should know how you are going to decide which is major and which is minor, right? So we are done with the analytical part. Whatever are the required for the analytical part, there are few theorems which we need to prove, which will be dealing in next sessions, and thereafter we will be starting with the numerical part, right? So thank you, that's it for today's session. Hope things are clear. Have a good day.